Well, last time we were together, we solved the question of the day that asked us to find the areas of these shapes. And if you recall, we found that the area of this triangle was equal to 1/2 the base times the height, which in our case, it was 1/2 of c times k. And then for the second one with the trapezoid, we found that the area was equal to the average of the bases times the height. In our case, for this problem, the bases are f and p, so the area would be 1/2 of f plus p, and then our base is actually z. And the reason we introduced these shapes was not just for geometry refreshers, but for the fact that we used areas when we were learning more about how to solve problems from velocity versus time graphs. We know that the slope represents the acceleration, and we reminded ourselves that from a velocity versus time graph, the displacement is from the area. And so by reminding us about what these different shapes have as their properties, we can calculate the area to determine the displacement of an object experiencing accelerated motion. But today what I want to introduce to you is, there are some times when a graph is actually the best and easiest way to solve a problem. But there are going to be times when you might want to lean on an equation in solving an accelerated motion problem. So what I'm going to do today is actually introduce you to a variety of equations, some of which you've already seen and some of which you haven't, that altogether help elaborate our model for accelerated motion. So as a reminder, when we had a velocity versus time graph, that was our initial velocity. This is our final velocity that corresponds to this. And this really is our amount of time. From our board meeting, remember we defined acceleration as the slope of this graph. When you think about the form of y equals mx plus b, slope-intercept form, we said in our board meeting that the final velocity is equal to the acceleration change in t times change in time plus the initial velocity. This was our first equation for accelerated motion in terms of velocity. So that's an important one. We're going to use that again in a little while. And what I'd like to do now, though, is I'd like to actually talk about how we can determine displacement from this graph, knowing again that we have the initial velocity, the final velocity, and then our time is the base of this shape. I'm going to ask you to find the area of this shaded region, and if you find it, see if you can find it a second way. I'm going to have you pause the video now so that you can actually come up with two representations for the area of this shaded region. When you are ready to resume the video, please go ahead and restart. So hopefully you have come up with two ways to actually express this area based on the variables I've given. I think probably one of the more common ways would be to take this and break it up into two shapes, a rectangle and a triangle. So if we were to do that, we could actually then find the area of each of these shapes, and together that would give us our displacement. So let's do that. Let's add the areas of these two shapes. It looks like that since area is equal to displacement, our rectangle has a height of v0 and a base of delta t. That's our rectangle. And then the formula for the area of the triangle is 1/2 the base, our base is delta t, times the height of our triangle. Over here our height is this distance, so it would be the top value minus this. So vf, or v minus the initial velocity. So this is the area of our triangle. Now, what you'll see in textbooks or things online is that they sometimes simplify this portion of the expression. And here's how they do that. If you go back to our equation that we first mentioned, v equals a delta t plus v0, if you subtract v0 from each side, what you'll notice is that this is now stated as being equivalent to that. And as a result, people will often substitute this portion in up here. And so this expression then actually becomes delta x equals v0 times delta t plus 1/2 delta t times our new quantity, a delta t. And when you simplify that, v0t plus 1/2 a delta t squared. This is our second equation for accelerated motion. Those of you who are paying close attention might realize this triangle is what our graph looked like in the board meeting, and that is what we had when we linearized the position versus time squared graph. If you remember, the slope was 1/2 a. So this should look somewhat familiar to you. Go ahead and take a moment to pause the video to make sure you have this copied down and think about how our area of the rectangle and the triangle work together to give us this equation for displacement. When you are ready, resume the video. So we have shown you one equation for displacement, finding the area of that shaded region. I wanted to show you another way that students sometimes think about, and that is when they actually recognize that this is a trapezoid. And when you know that this is a trapezoid, you can use the trapezoid formula to figure out what the displacement actually is. So displacement, since that's the area of this graph, is going to equal 1/2 of the bases. We've got v0, and then the other base is the velocity, and then the base, or the height in this case, would actually be delta t. So sometimes this is written as v plus v0 over 2 times delta t. This is another way to think about the area of this shape. If you're wondering how that works, when you really are finding the average of these two quantities, v and v0, you're really locating what the midpoint of those two is. So if you think about it here, you're kind of identifying where that middle spot is, and then you're kind of clipping this trapezoid and taking that top segment and now making a rectangle that has a height that's equal to the average of the two bases. So geometrically, that's how it works. But this is our second equation for displacement for accelerated motion, and it's coming from the trapezoid formula. Make sure you have this copied down as well. And when you're ready to resume, go ahead and continue playing. I am going to ask you to pause the video so that you can follow along. So we have introduced 3 formulas so far, and 2 of them I am showing you right now. This V0, the velocity equation that we mentioned, and this displacement equation that we have here. I'd like to actually show you how we can combine these two to make another equation, and why we need another equation will become clear in just a moment. You do not have to copy this down. I just want you to follow along so that you know kind of where this comes from. That's what's most important. I'm going to start over here at this velocity equation, and I'm going to subtract v0 from each side, and that's going to leave me with v minus v0 equals a delta t. And now I'm going to divide both sides by acceleration, and the acceleration term will divide out. So now I have this expression for delta t. Basically that v minus v0 over a is equivalent to the amount of time. Now what I'm going to do is I'm going to take this expression for delta t, and I'm actually going to put it in here. And what we're doing now is we're getting rid of any time in the equation. So v plus v0 over 2 times v minus v0 over a. And I'm going to actually now do a little bit of algebra. I'm going to start off by the denominators. 2 times a is 2a. Now the numerators, I've got to actually FOIL this. It says v squared plus v0, that's the outer. Actually, the outer would be it'd be minus v0. See that now. So v squared, outer would be minus v0, then plus v0, and then minus v0 squared. That's right. Okay. Now we can go ahead, and this v0 times v is negative here, and v times v0 is positive. Those are going to add up to 0. And so my expression is going to be delta x equals v squared minus v0 squared over 2a. And just going to rearrange this a little bit. Multiply both sides by 2a equals v squared minus v0 squared. And now, when you look in a book or you look online, your formula is going to look like this. V squared equals v initial squared plus 2 times the acceleration times the displacement. This is our fourth and our final equation for accelerated motion. Again, the value in this is that there is not a term for time. Okay? All right, that's a lot. That's a lot. Now, what we're going to do is we're going to actually try to synthesize this into a table. So I'd like you to take a couple minutes. We'll pause the video and give you a chance to draw this chart into your notebooks. When you are done drawing all the lines and all the column headings, we'll go ahead and fill it out. So go ahead and pause the video now, and once you have the chart drawn, feel free to resume the video. All right, so we have our equation summary here. We're going to list all of our equations and go ahead and try to come up with a useful way to keep track of these. Our first equation was v equals a delta t plus v sub 0. The variables, or the letters that are there, are v, acceleration, time, and v sub 0. But there is no term about displacement in that equation. So if you're asked for displacement, don't use that equation right away unless this is a multi-step problem. But this is what we're looking at here. Our second equation was displacement, v0 times time plus 1/2 a delta t squared. The variables that are in this one are displacement, initial velocity, time, and acceleration. There is no final velocity listed in that equation. We had another displacement equation, and this was v plus v0 over 2 times t. The variables present in that were displacement, initial velocity, or final velocity, initial velocity, and time. No mention of the actual acceleration term in that equation. And then the derivation was v squared equals v0 squared plus 2 acceleration times displacement. We have final velocity, initial velocity, acceleration, and displacement. There is no delta t. So, ladies and gentlemen, these are the reasons why we have 4 equations, because there are so many more variables in this type of motion. We need more equations to be able to solve for the different possibilities. So you're going to now be asked to try to apply these using the guess method. Identify your given, really look for what you're trying to solve for, see if there's a representation, an equation that works, and then begin working through these. Practice is what's going to lead you to success. Good luck.